Thank you very much for coming to my talk. My name is Michael Armbrust. I'm a Spark contributor that works at Databricks, and I'm the kind of initial author of Spark SQL. And I'm here to talk to you about a project that basically began when we committed Spark SQL.
Your microphone
is cutting out, isn't it? Yeah. Hey, can we check that? But it's still cutting out. Okay. How's that? That's pretty good? Cool. Okay. Take two. I'm here to talk today about a project that started a while ago, back when we first committed Spark SQL to the Apache repository. I guess that was about a year and a half ago. It's been kind of a continual quest to provide more structure to Spark through a variety of higher level APIs. But before we dive into that, I kind of want to start with some background material on what was there before we began this initiative. And so kind of in order to dive into that, we need to look at what does Spark see when it sees an RDD or when it sees a set of RDD operations. So basically there's three things that define an RDD to Spark. One of them is the dependencies. So this is other RDDs that need to be calculated in order for this RDD to be calculated. So inputs to a join or other things like that. Additionally, the RDD needs to tell Spark about its own partitioning. So it says, I can split up this task into this many pieces. Here is metadata about each of those pieces so that I know which piece it is. And it can also have optional locality info. So for example, if you're reading files off of HDFS, it can say, it would be nice if I was scheduled on that machine. I'll run much faster if I'm doing a local read instead of reading it over the network. And then finally, kind of the core of an RDD is this thing called the compute function. And a compute function is pretty simple. Spark gives it one of the partitions and says, give me an iterator of your data type. So you just have to produce all of the items for that partition in this compute function. So this is pretty good, and it turns out it's an incredibly general model. You can build all kinds of things on top of this. We built SQL, we've built streaming, we've built graph processing, all on the RDD model. But there are some limitations that make it not great from an optimization standpoint. In particular, this function here that is actually doing the computation is completely opaque to Spark. We don't know what's going on the inside, and so we can't change it. If we're afraid that if we make any changes to it, we might change the answer, and we certainly don't want to do that. And in addition to the function being opaque, the data type that comes out is also opaque. It's just a blob of bytes to us. We don't know its structure. We don't know the best way to compress it or other things like that. We don't know if your function is only using a subset of the fields inside of your object. And so as a result, we're limited in what we can do. And so as a result, we've decided to kind of try and add structure. And so what do I mean when I talk about structure? I mean, really, there's a pattern. There's an organization. We have these high-level constructs that you're using instead of this incredibly generic high-level interface, right? So I know this is a filter. I know this is a projection. I know you're doing a join, and I know the conditions of that join. And so through the rest of this talk, I'm going to be describing the ways in which some of the higher level APIs on Spark allow you to tell Spark about the kind of natural structure of your program that already exists, and then allow Spark to do better optimizations as a result. So the question is, why structure? Because by definition, this is going to limit what you can express, right? I'm not going to give you just completely arbitrary anything anymore. Although I will say that's not totally true, because you can always go back to RDDs, which I think is actually the real power of this model. But in many cases, if you are using the higher level APIs, you're a little bit restricted in what you can do. But in practice, it turns out that a vast majority of computations can still be expressed with this limited vocabulary. And what that means is by limiting the space of what can be expressed, we have this potential for optimizations. And now this one cut out. I'll just talk loud for now. So there's a bunch of different structured APIs in Spark. We started initially with SQL, and okay, is it working now? Okay, we started initially with SQL. That was the first one. And I kind of view this as a spectrum of different APIs that give you different guarantees. So SQL is the most flexible, and datasets is the most restrictive. And kind of the way, at least that I approach this problem, is by thinking about, what kinds of guarantees am I getting from the API itself? I think there's kind of two types of errors that different APIs will protect you from as a programmer. So one of them is syntax errors. This is like I make a spelling mistake, I forget a comma, et cetera. So with SQL, that's going to be runtime. To the Scala compiler or to the Java compiler, it's just a string that you're passing to the SQL engine. And so there's no way for it to know. And analysis errors are, I have a data type mismatch, or I'm asking for a column that doesn't exist. Same thing. Until I actually try to execute that query, I'm not going to know that it's missing. Data frames bring you a little bit closer to the full compile time safety. Because if I call a function on a data frame that doesn't exist, the Scala compiler knows. It's going to tell you that this is a mistake. But still, there's a bunch of strings that I'm passing into that function that are representing column names. And if one of those is missing or it's of the wrong type, you're not going to find out until the end. And then finally, data sets, the newest API, it's Lambda functions, it's objects. The Scala compiler knows everything that's going on, at least as far as the actual data set part of it. And so you get compile time safety in both cases. However, an important thing to realize is in any of these cases, no matter which API you're using, analysis errors are always going to be reported before a distributed job begins. So this is still more power than what you're getting from RDDs, right? With RDDs, if there's a mistake inside of that compute function, you may have processed terabytes of data before the exception is thrown. So in any case, all of these higher level APIs give you better type safety. So I've been talking about this dataset API, but I want to kind of dive into some of the details about what it looks like and what you can do with it, since it's one of the newest things that we've added to Spark. One of the high-level goals here of datasets was to give a type-safe API that let you use your own domain objects that your libraries are expecting. So for those of you who saw the demo of Databricks Community Edition yesterday, we actually took a library that was expecting a specific object type, and what datasets let us do is map to that object type automatically. So one example here is we can read in a data frame, and at this point we don't know the schema of that data frame. But we can then cast it into a person and call Lambda functions with it. And so it's going to do some mapping there. And I'll go into more details about exactly what's happening under the covers later in the talk. And then finally, I think this is where it's very powerful. There are some things that are easy to express with relational algebra. There are some things that are much easier to express with imperative programming. And so having both of these lets you kind of do something like a histogram, which is much easier to express just with Scala or Java code than in relational algebra. So this mixing of the worlds, I think, kind of where the dataset API becomes very powerful. So another thing, though, is now people are saying, wait a second, there's a lot of concepts for me to deal with. And we want to keep Spark very simple. And so in Spark 2.0, our plan is to unify these APIs. So really, you have one concept to deal with. It is this data frame, or it is a data set. But it's a single type of object. You can pass either one to any library that you're going to be working with. MLlib will be agnostic to which one you're passing it, for example. And I think the way to think about this is, anytime, you can think of a data frame as just a data set of generic row objects. So it does have a type, but those rows are not something the compiler knows a ton of information. And anytime I call one of these, I'll call them stringly typed methods, where I'm just passing to the method a bunch of strings that the compiler doesn't understand, all it's going to do is it's just going to kind of downcast it and give you generic row objects. But if you want type safety, if you want to work with your own specific objects, all you have to do is tell the compiler that. So say, as my, and what that's going to do is it's going to enforce a contract at that moment and say, Spark will check, make sure the columns line up, and all code after that point, you will be ensured type safety. So of course we can't know ahead of time because we don't have access to the JSON file that we're reading. But anything past that will be validated. So I think this is a pretty nice balance. So a lot of you might be saying, wait a second, what about Python? I thought Python was an important part of Spark. And it totally is. And I think an important thing to realize here is a lot of the goals of the dataset API have always been available in Python. As a dynamically typed language, you could kind of get away with writing things in a very concise way. One of the key benefits, automatically. So consider something like this, where I take a data frame and I go into a map function. Today, before Spark 1.5, before we released the dataset API, you would have to remember which column was the field you were looking for, and you would have to do typecast to get it to be the type that you actually wanted. And in Python, you could always just do this, because everything is dynamic. It's being evaluated at runtime.
Put the mic in your front. Sorry, the backpack.
Yeah.
Let's see if that helps.
OK.
Sorry, guys.
Yeah. So, okay, we'll try that. So basically, you've always had these benefits in Python. And so what we are going to try to do is we are going to try to make it as easy as possible to go back and forth between objects that your Python program understands and data frames where we understand the full structure. And so I think the coolest part about all of this, though, is whether you're using SQL, whether you're using data frames, whether you're using data sets, whether you're coding in Scala, Java, Python, or R, it is the same optimization pathway underneath the covers. So all of the work that's being done in Catalyst, all of the work that's being done in Tungsten, you kind of automatically get those benefits no matter which API you're using. So those of you who saw Nong's talk yesterday on full stage code gen, all of those benefits will be realized independent of the language that you're coding in. So now I want to go into some of the kind of nitty-gritty details of the different ways that you can structure things in a way that Spark understands. I'm going to start by talking about computation. An important thing to realize, the kind of the key construct here when it comes to structuring computation is this notion of a column. The way you can think of a column is some value that Spark is going to compute based on some input values. So for example, with the DSL in either in Scala or Java, you can just say column X equals 1. Or you can say column X on a specific data frame equals 1. But you can also do the same using the SQL parser. So expression, and then you can give it any SQL expression, and it will parse it and return a column object to you for that expression. Or you can even do entire SQL strings. And I think the important thing to realize here is all of these are doing exactly the same thing under the covers. So it's really just whichever one is allowing you to express the construct that you want most efficiently. And I actually, when I'm programming, often go back and forth. For simple things like this, I prefer the DSL. But if I'm going to do something complicated like window functions, it actually turns out that's easier for me to express in SQL. But it's really up to you as the developer to pick the API that is the most natural for the problem you're solving, and understand that it's the same underneath no matter what. The cool thing about columns, though, is it's more than just this simple equality. You can actually construct relatively complex expressions. So if you want to do string manipulation and concatenation, if you want to do math and arithmetic, if you want to do even kind of distributed operations, like calculating a monotonically increasing ID that is unique to all of the objects in your data set, you can use all of those as column expressions too, and they're composable. And the nice thing here is when you're using these complex expressions, when it actually runs, we are generating efficient bytecode to do that operation, no matter which programming language you're writing in. This Python program and this Scala program are going to end up generating the same bytecode underneath the covers. So, but why is this important? Why is this different than Lambda functions? The important thing to realize is, well, the thing that you type may look very similar to you as a developer. What Spark is able to understand about it is actually quite a bit different. In the first case where we have a function that's just saying does x equal 1, all Spark sees is this opaque class that takes in an integer and returns a Boolean. And we have no idea what you're doing inside of there. You could be flipping a coin for all we know. And when you have a column, though, we actually parse that, and we understand the semantic relationship that you were saying x equals 1. And in the next slides, I'm going to talk about some cases where that actually allows us to do things differently. So one example is predicate pushdown. So if you looked at this data frame code, let me kind of unpack it a little bit first. In the top part, I am connecting to a Postgres JDBC database and loading it as a data frame. And then I'm going to apply a filter there where I say, well, I only care about users where the name equals Michael. So this looks pretty cool. And the nice thing is, because Spark actually understands that where clause, we know that it's equality, we can actually rewrite it into equivalent SQL that we then transmit to Postgres, allowing Postgres to do the filtering and processing before the data even comes to Spark. If that was opaque Java bytecode or Python code, we couldn't do that translation automatically. Another example that I've actually seen confusion on the Spark user list several times for is computing joins. So consider this case where I've got two data frames, and I want to do a join based on some UDF. So in this case, all the UDF is doing is comparing x equals y. You pass this to Spark, and you pass it two columns. But we don't know what's going on underneath the covers. So the only way for us to evaluate this join correctly is to actually compute every possible combination of objects and then apply it to your filter. And so this is then going to end up being an n-squared operation. In contrast, if you tell us, I want to compute x equals y, we're going to realize a property of equality, which is equal values are always going to sort to the same place. And so we'll sort the data set and do a much more efficient n log n algorithm in order to compute the join here. So that was computation, but it's actually more than just the work of transforming data. It's even just the representation of data where structure can help. So before I get into that, I want to talk just a little bit about what Spark's data model looks like. For those of you who've used Spark SQL, or even other systems like Avro or Parquet, they should look pretty similar. But basically, Spark has a pretty flexible type system. We've got a bunch of primitive types, including all the numeric types, strings, as well as things like timestamp and dates. And then these things are composable, so I can turn them into arrays, I can turn them into structs, I can turn them into maps. Another question that I often get is, when should I use a struct and when should I use a map? What is the difference between those things? A thing to realize here is that when you have a struct, that is a fixed number of columns where I know all of the columns ahead of time, and they might have different types. In contrast, a map is from a single type to a single type, but you can have an arbitrary set of things. So an example here is like if I have a bunch of tags and there's a million possible different tags that I might have, it's probably more efficient to use a map because not every record has the same set of tags. But if every record is going to have a fairly fixed subset of things, then a struct probably makes more sense. So, but the nice thing about having this restricted type system is now that we know all of the types, we can actually do encoding. We can take that data and we can put it into Tungsten's compact binary format. And this is where a new concept that is part of the Dataset API comes in, called encoders. The job of an encoder is to take your JVM object and translate it into the internal representation. And this is actually a pretty powerful concept because what it means is now all of the data types that Spark supports can automatically be mapped into your custom type. So in this example, I'm taking some JSON data and I'm mapping it into a case class. But this also works with Java Beans or any object where you have an encoder that is present. And the nice thing is it's actually doing an intelligent mapping here. It's doing it based on name. So you'll notice language and zip are flipped here, but Spark is actually going to figure that out. And if there's a mismatch, it's going to tell you early before any processing begins to occur. And it's not just about eliminating boilerplate. It's actually significantly more efficient than the equivalent caching that you would get if you were using just kind of simple Java serialization in order to do caching. So this is a comparison of using encoders to cache a bunch of string data with using RDDs to cache a bunch of string data. We can actually do a much more compact encoding because we understand this is just a bunch of strings. We store them exactly back to back without having a bunch of object header information. And as a result, it ends up being significantly better. And it's not just about space. It's actually about speed as well. So a lot of people try to use the Cryo serializer instead of the Java serializer because it's faster. But it turns out encoders are actually generated at runtime for your specific class. So it is as efficient as if you were handwriting code to do the serialization and deserialization. And another nice thing here is because that internal format is something that we understand, you can actually often operate without even doing a deserialization. So there's two different ways I could write this function here, right? I could write dfwhere, I could give it a lambda function, or I could write dfwhere and give it a column expression. The reason it's nice to give it a column expression is because what's going to happen underneath the covers is, again, we're going to translate this into an expression that we understand, and then we're going to generate this efficient bytecode that actually operates directly on the serialized data without ever doing an object allocation. And this is actually even better than it looks because the JVM is going to do a really good job of JITting it. And things like that platform getInt actually get JITted down to what's called an intrinsic. So it's not even going to be a function call. It's just going to be pointer arithmetic, as though I was writing low-level C++ code. So this is pretty cool because you can actually kind of feed data through Spark, turn it into objects when you want to operate on it, but let Spark do a lot of the bread and butter filtering and processing automatically. So that's kind of a whirlwind tour of data frames and data sets. But I want to really quickly go through another thing, which is streaming. For those of you who saw the keynote, some of this might look familiar, but I just want to tie it back to this. Because again, it is all of this extra structure information that allows us to make streaming easier. So as Reynolds said this morning, the easiest way to perform streaming is don't think about the fact that it's streaming. You just want to view it as either a static table, where you know all of the data ahead of time, or as an infinite table where data is continuously arriving. And you should be able to use the same API either way. And so kind of our goal with this project is to build a higher level streaming engine where we actually do the incrementalization for you. And I think the nice thing here, especially as we push forward with this, is I think we can actually have a lot of kind of nice constructs. For example, updating databases, changing queries at runtime, and even things like integration with MLlib, where all this structure allows us to do a much better job automatically. So just to walk through an example, which you probably saw this morning, we've got a bunch of log data that we're reading. We're going to perform an aggregation, and we're going to save it out to JDBC. This is great if the data is there and no more is going to arrive. But if people continually are dumping more JSON logs into this S3 bucket, I want to change it into a continuous stream. I want to say just keep running this over and over again as new data arrives. And what's happening here is that data frame is getting turned into a logical plan, and then Catalyst is doing this optimization to figure out how to incrementalize it. And so what that looks like, by using that structure, we can figure out that in the batch case, we would just scan all the files. Whereas in the incremental case, we need to scan only the new files. For aggregation, you can do a one-shot version, or you can actually keep the aggregates around and update them incrementally in a stateful way. And finally, you can either do just a blind write, or you can actually do intelligent updates. And because we understand what's going on in the query, we can do this automatically without you having to write the code. This is something that wouldn't be possible with the dstream API. So, in conclusion, I'm pretty excited about the direction of these APIs and where they're going and how I think they're enabling, more efficient development on top of Spark. So there's a bunch of cool stuff in the pipeline. For Spark 2.0, our goal is to really have a nice kind of stable foundation for the rest of the 2x series to build on top of. So we want to simplify concepts, we want to unify APIs, and we want to put the basics of streaming out there for people to start using. And we also want to get a good idea of what some of the more complicated things like event time are going to look like. And then finally, in Spark 2.1, I think we're going to continue to expand this. Have other sources and sinks, the ability to write to databases, the ability to update Cassandra, and also integration with things like machine learning. And I think another kind of complementary thing that you're going to be seeing is more and more libraries are going to be taking advantage of this structured data. So MLlib has already switched almost entirely to using data frames for pipelines. There's another talk this afternoon on a project called GraphFrames, which is GraphX, but reimagined on top of data frames. And so I think this is going to be a trend moving forward. So with that, I'm happy to take questions with the little time that's remaining. Thank you very much.
I'd like to thank Michael. Oh, okay. Try a different one. I'd like to thank Michael for his great presentation. If we can turn on the mics back here, and you can ask your questions. Raise your hand, please, and you can ask questions.
My question is regarding.
I can hear you.
My question is regarding PySpark.
Yes.
So would you please explain a little bit about the map and reduce function? Okay. My question is on PySpark. Would you please explain a little bit on any collision between Python map and reduce and Spark map and reduce for future purpose?
Yeah, so I guess with PySpark, our goal is to basically make it possible to continue to do MapReduce style computations using whatever Python objects you want. And by default, when you do that, since the Python interpreter doesn't know any types there, it can't give us any information, it will look to Spark like an opaque blob of bytes. But if you are willing to tell us the schema, if you want to say the column names and the names, it will be kind of seamless to translate it into a data frame so you can switch and do operations kind of in the more efficient JVM world. But really we want to provide a nice balance where you pick the API that you want to write in. Is there, either one? Which one day you can get to?
I can shout actually. Okay, so you mentioned raw RDDs versus data frames or data sets in future. So between RDD and data sets, it's pretty clear, you explained. But what are the comparison of raw versus structured data sets? Is there any kind of optimization? Because again, in some cases, it's nice to have some real-time flexibility versus compile time flexibility in data structures.
Yeah.
But we still need some performance improvements.
That's a great question. I mean, so I think one thing to realize is data sets and data frames are actually exactly the same thing under the covers. The The turning it into an object is a last minute thing that we do just before calling your Lambda function. And internally, all of the data is stored the same way. So there are no performance implications to going one way or the other. And with that, I think I'm going to let the next speaker go. But I have office hours at the Databricks booth from 12 to 2 o'clock if there are more questions. Thank you very much.